Today I'm going to be discussing how I could improve the population of annoying frogs that hang out in my backyard. And since we've drained our pool, they've been getting stuck in there and for whatever reason cannot get themselves out, and they get super loud at night. So hopefully I'll improve the population by increasing the length of their hind legs so they can get out of the pool and out of the backyard. The broad sense heritability, uppercase H squared, of hind leg length in frogs is 0.85, and the realized heritability, lowercase h squared, is 0.67. The mean hind leg length of my original population, represented by x naught, is 12 millimeters, which is just less than half an inch, with a standard deviation represented by sigma of 5 millimeters. In order to select for the top 10%, we need to find the truncation point, represented by x sub t. This is found by using the mean of our original population, x naught, and the standard deviation, sigma, and a value from this table called the standardized selection point, aka z. The truncation point formula is x naught plus z times sigma. We use 1.282 for z in this example because it corresponds to the 0.1 column on the table, which means we're selecting the top 10%. Our result for truncation point will be 18.41, and once we've found that, we need to find selection differential, or S. In this part, we use another value from the table, the selection intensity, or I. The selection differential formula is I times sigma, and we use 1.755 for I since it corresponds with the 0.1 column. The result from this formula will be 8.755. And since I'm trying to improve my population, I want to know the response to selection, or R. The formula for this will be realized heritability times selection differential. Our lowercase h squared, as I mentioned earlier, is 0.67, and multiplied times the s, 8.755, we get a response to selection of 5.866. When we add the r to x naught, we get 17.866, and that represents the mean of the offspring population. And if we want to know the average hind leg length of the parents I selected, we can add the s to x naught, which would equal 20.755. The histogram seen here includes all of the values I just discussed. The pink-colored solid curve represents the hind leg length of the original population of backyard frogs. This point here at 12 millimeters is x naught, or the mean hind leg length of my original population. The dotted yellow curve represents the hind leg length of the offspring population, and this dotted line is x sub 1, or mean hind leg length of offspring. The distance between these two is the response to selection. This line represents the truncation point at 18.41 millimeters, and the region is the mean hind leg length of selected parents, or x sub s, and the distance between that and the original mean is the selection differential. Unfortunately, I wouldn't be able to continue this style of breeding for my backyard frogs forever because they would reach a threshold where they could not survive because their legs would be so long. The greater the leg length, the more difficult mating would be and the less proportional their bodies would be. So passing that threshold would be inhumane and the frogs wouldn't be able to survive with such long legs.